attempt to do that. But that is now starting. So all of that work is now just saved on there in the video. And now this weird talk over, but not the walk up to those, all that work. For each of the subsequent ones, I will go through and do that, and I'll try and make sure they actually get recorded.
Yeah, so. I thought last time it gave me the option to record it myself, but it's grayed out, so I was just curious.
I have no idea how to alter that. That's weird. I don't know what to say about that. I am going to go ahead and pause the recording, though.
Because I was trying to make it look like the finished product.
And you say that in kind of a joking manner, and I'm also going to add another statement here. I am recording now, so you may get recorded if that's okay with you.
Oh, yeah. No, that's fine.
One of the things that you should like about mechanisms, you just have to make it happen. So you may not agree with what's going to happen, but a perfectly valid attempt is that you know that that has to happen. So just do it. Okay? So if that happens, that has to break. And the end result, and I'm going to spin it on its side, is that we're now going to form a bond out to our carbon. What's left over is you get the Br minus left over as a byproduct or a side product of this reaction. And then, yeah, that's it.
All right, cool. I was just nervous that I was just kind of making a big stretch with that.
Nope. That is exactly what it should be. So mechanisms are nice if you understand curved arrows. Okay? So because I know Kendra's been looking at it, there's that book that I recommended at the beginning of the semester, the Pushing Electrons book. What that one's trying to do is get you comfortable with how electrons move. That's curved arrows. So a mechanism, you just have to make it happen. You do have to make it happen in the proper kind of sequencing behind it. So, for example, I have seen students attempt something along these lines. I'm just going to say that's a ring. Minus. Sorry, it's a little bit crowded down there. And I've seen students try and do this. Well, it goes this, then this, then this, and then this. And then, ta-da, we've got our final product. Okay. Well, one of the reasons why I like Cardi so much is that it has that chapter 7 of here are the basic mechanistic steps. Okay. So we're looking at two potential quote-unquote mechanisms for this, A versus B. Okay. Well, in A, what was the breakdown of our mechanistic steps? Well, that very first step was an acid-base step. Is that a valid mechanistic step? Yeah, acid-base was. Okay. Oh, that's not an arrow there. Sorry. The next step was an SN2 mechanism. Is an SN2 mechanistic step a valid mechanism? Yeah, it is. Now take a look at B. Can all of that happen at once? What mechanism allows that to occur? It doesn't, which means B is an invalid answer. It doesn't actually show mechanistic steps. So when you're going through and trying to do a mechanism, you're just trying to evaluate the flow of electrons. Both of these show the flow of electrons, but you're also now adding in when are you allowed to address that flow of electrons? When are those things allowed to happen? Those allowances are chapter 7 mechanistic steps. So when you look at an individual step in your drawn out reaction, it had better match the patterns addressed in chapter 7. If they don't address those patterns, then what you have drawn is something that is invalid. Oh, that was not the button I thought it was. One of the things we can do, I'm I'm pretty sure I can undo this, is addressed what changed between the reaction. So what are our changes? Okay. Well, we have two potential changes, H loss or O loss. Okay. Because we don't know necessarily which one was formed at the end result. Okay. We also then potentially have an OC bond formed, or I guess we'll call it O phenyl ring formed, or an OC bond formed. So all of those things have to happen. Deciding when and how those things happen becomes the important part. So what you want to do is look for those changes and then decide based off those reagents, what does that mean? Step 1, we were given hydroxide, which means that H bond breaking is probably going to happen because of the hydroxide. Okay? In step 2, we were given that carbon-carbon, which means this is probably happening with that reagent. Okay? Which means these two things aren't happening. Now we can address, using our curved arrows, each of those changes. Okay? I need to remove the H. Whoops, come on. Remove the H, which means the electrons, man, that looks awful. Which means the electrons will now go to that oxygen. What does that result in? What does that look like? This is why drawing out those structures can come in handy, because you can now see those pieces and you can now start to evaluate what's happening at each of those stages. We've now addressed everything in red. So we could do the purple ones. And the purple ones, we wanted to form the bond between our oxygen and that carbon. Why should that carbon react? Well, bromine's a good leaving group. It's going to withdraw those electrons. So what would that result in? Okay? And as you go through and kind of think about the reactivity of those things changing, you also need to keep in mind of where you're ending. So now I've got a black structure drawn based off of where those charges were. Is that what I wanted to get at the end? Well, it was, which means I'm done. There's the mechanism. Okay? So it's that thought process behind how you move through it that you're trying to show in these kind of show your work processes. That's what the mechanism is showing. How do you think this thing is supposed to happen? There are certain ways that you're allowed to do things, okay? Which is true for everything. So in question 16, this is for the recording's sake, I'm okay with you saying A is bad because we're taking electrons from a pi bond and going to an electron-rich atom. That is problematic. Okay, so that in and of itself should be a good reason to eliminate that as an answer. If we take a look at B, you're going again from a pi bond, but now you're going to a hydrogen. Note the electrons are being drawn away. That hydrogen, as a strong acid, I'll rewrite that here. As a strong acid, it's a little bit better, is electron poor. Okay, so that arrow makes sense. That arrow is okay. If we go through and look at C, we're going from a negative, okay, to that carbon. Okay, so you're going from electrons, electron rich, and now to that carbon. That carbon is actually electron poor. Why is that carbon electron poor?
Because of the pi bond?
Not so much the pi bond.
Oh, it's the cyclotriangle, or the triangle?
Nope.
Okay, I have no idea.
The oxygen.
Oh wait, hold on. It's the polar from the. It's polar because of the oxygen.
Yeah. The carbon is electron poor in C, just like the hydrogen was electron poor in B. They're electron poor for the same reason. They're connected to an electronegative element, which is withdrawing electrons. So both of those are showing the proper directionality of the curved arrows. Electrons moving towards an electron poor element. So both of those are acceptable. If we go through, and we'll come back to that in a second, if we go through and look at D, you're going from electron rich, your pi bond, towards that oxygen. That's electrons towards electrons. For the same reason that A was bad, D is also bad. Okay, so I can accept the explanation for those two. I'm not following your explanation for why C is a bad mechanistic step right now, though, because the electrons are moving to an electron poor area. Anybody else have any ideas? So silence hopefully means no, and not that I have somehow disconnected from the internet. Okay, so let's go through. When in doubt, draw it out. Draw the result of that arrow. Okay, there's only one arrow shown. Nothing happened to the ring, so I'm going to leave that alone. Nothing happened to the pi bond, so I'm going to leave that alone. And then we have this new bond to the sulfur, which I'll show in green. There's our new bond to the sulfur, which is then connected out to those. What is bad about that arrow? That the mechanistic step has to result in a valid structure. Is that structure valid?
No, it has a full octet. So when do you know if you can move the electrons from the pi bond up to the oxygen and when you can't?
So, when can you? Whenever you want. Yep. In this case, if you moved them, this would be a valid mechanism. Did you move them though? So if we look at what C shows, you can only do what your arrows show to be a valid, acceptable mechanistic step. There is no arrow showing that pi bond breaks, which means you can't touch it. You have to leave it alone. So that is an unacceptable mechanistic step because we've exceeded the octet. How do we make it a valid mechanistic step? We would have to add an arrow. Okay, so that's good. You recognize how you can fix it. That's phenomenal because that will now help you when you're drawing out a mechanism. You go, oh, well, this is a bad mechanism. You can fix that. You don't miss silly points like this. Okay, but the whole point of mechanisms and those curved arrows is that you do exactly what they show. Nothing more and nothing less. Okay? So C is an invalid mechanistic step because it results in a structure that has exceeded the octet. Okay? And then that's why we should be crossing out C. Which then means B, which is where I believe Robert was going with it anyway. B is the correct answer. And B is a better answer because we haven't exceeded any octets. That initial arrow movement of the pi bond reacting with the hydrogen does exceed the octet of the hydrogen, but we very swiftly fixed that by adding another curved arrow showing the electrons moving away from the hydrogen. And that's why that is a valid mechanistic step. Okay? So I think we've covered that one. What I'm going to jump to is in the chat. Hassan's asked a question about, in terms of difficulty, how much harder is the exam going to be? I did go through and build the exam. It is entirely done, beginning to end, multiple choice and show your work, so those totals are up there. Harder becomes a difficult question to answer. What I can say is that the easy questions, where those easy questions are the easiest way for me to reference it would be Gen Chem kind of questions. What is the formula for sodium phosphate? That level question won't show up, okay? Because that is a very easy thing to copy and paste into Google. So virtually all of your questions are things that you can't copy and paste into Google easily. Okay? So that's where I think the big difference is. Most of your exam questions, if you go back and look at old exams, it's rare for really any question to be strictly Googleable. Okay? And that's the thing that I've kind of had to adjust. So if we look at practice exam 3, Sorry, as I'm going to try and scroll through. Arguably this one, question 8, is kind of a Googleable question. Even then, for you guys, a lot of your questions aren't super... I'm really not liking how Googleable sounds. Aren't easily done that way. You could copy and paste this into Google, and what it will show you would be an example of an acid-base mechanistic step. It doesn't show you the answer here, it shows you the example of it. So this one gets kind of borderline. You could Google that really easily as a question that doesn't necessarily help you answer the question. So I would probably say that one's okay. There we go. What type of solvent is ethanol? If you type that into Google and hit go, it's going to tell you the answer. Okay? I'm actually not positive on that, but let's take a look. Right out of the gate, polar protic. Okay, so that question, there it is. That question is kind of a dumb question for me to ask because you've advanced through coursework enough that you could easily Google that answer or recognize that as an easily Googleable answer. When you don't have the internet as your guide, you would have to be able to know what these terms meant to answer that on a test in class. Okay? So in a class test, I have no problems asking this question because you have to think about it. On an online exam, you don't have to think that hard. You don't have to think about this question really at all. You could just copy and paste it into Google and you get your answer. So I'm going to make the argument that that question isn't going to show up on the exam. It doesn't mean it isn't. It just means it's not a good question for me to ask. But if we go through and look at these other ones, okay, you can Google that question. That isn't going to do you jack because it has to apply to the reaction that you're looking at. Okay, so there's thought process. So a lot of the questions that you guys encounter in OChem immediately go to application with a structure drawn. So in my process of going through and writing the exam, I was actually surprised at how many questions I didn't have to pull from my test banks or remove from your potential exam because it required some understanding. You had to know something. Even this question with the solvent with ethanol, I would make the argument that if you actually knew the definitions, you can get that answer faster than if you Googled it. Okay? So sure, go ahead and Google it. You're now wasting time because now you won't be able to go and answer those other questions. So you should know your content just as much as you knew it in the past. Just realize that those kind of simple level questions won't show up. Provide the definitions. Yeah, I can't. That's not a useful question. Okay? That is going to be way too easy for someone to just copy and paste a definition from the internet in. Okay, so that kind of question is going to disappear. Okay, or at least show up to a very small percentage for a small percentage of time because the answer that you're going to give me shows nothing of your understanding of the material. And so the questions that are in the exam are designed, hopefully, to reflect your understanding. Okay, so the difficulty statement that I made in those past posts is, I don't think quite as fair or dramatic a statement as it sounded like. I think it's going to mimic pretty closely what you've seen already. I do. I hope. Okay. And I'm going to pause the recording again. Now we'll actually start the recording because the rest of it was technically textual. Why does an SN2 need a polar aprotic environment? Okay, so why is that necessary? So first off, what is our role of our solvent? What should the solvent do? The solvent needs to dissolve stuff. Okay? To dissolve stuff, this is looking at solubility. This is like forces, like forces. So we would have to go through and evaluate similar forces. Well, similar forces for what? If we're looking at dissolving for a chemical reaction, this needs to be our reactants. So we could go up and look at our reactants and determine their individual forces. Okay? For the alkyl halide, we're looking at dipole-dipole forces. For the nucleophile, we're looking at ionic forces. How do we know ionic? Sodium is a metal, okay, which means it has to be an ionic force. Okay? So for a solvent to dissolve both of those, it has to have some kind of intermolecular force that deals with both. Okay? Which means the apolar aprotic can't work. Okay? Because that's not similar to ionic and that's not similar to the dipole-dipole. The polar protic would work out fairly well for our ionic. The polar aprotic would work out fairly well for the dipole-dipole. Okay? Water is a specific example of polar protic, which should send up all sorts of alarm bells. Okay? What would those alarm bells be? Well, if water is an answer, that's a protic solvent, which would mean both A and D are valid answers. That's probably not true. Okay? Which means polar aprotic is probably what we want, not protic. Okay? So the question is going to now become, well, the why. Why would the polar protic not be a good choice? It dissolves the ionic compound very well. Wouldn't that be a good thing? Okay? Well, in an SN2 mechanism, everybody's favorite thing about to happen here, we are looking at a rate law. We've got the substrate and the nucleophile, okay, concentrations of those. What was probably mentioned as a one-off statement back in 152 that you likely just chose to ignore was that when we're looking at our rate laws, they aren't actually concentrations. They're activities of the individual substance. Okay, why is that important? For an SN2 reaction to occur, I need a highly active nucleophile. If I use a protic solvent, that protic solvent contributes H+. What is that protic H+ going to interact with? Well, the negative of the nucleophile. What is that going to do to the nucleophile? That's going to inactivate it. Instead of it being negative, it now becomes neutral in the presence of a protic solvent, which means the activity goes down, which means my rate goes down, which means not good for an SN2 reaction. Okay? We want our reactions to go as fast as we possibly can. Okay? So lots of kind of underlying content behind that individual question that really just boils down to, can you look at a reaction and decide what mechanism it is? If you can decide what mechanism it is, you can then categorize out for whatever context you're looking at. Substrate, nucleophile, solvent, and leaving group I'm just going to leave off because it's just not useful. So you're now categorizing based off of those three sections, which is why this question is ultimately originating from chapter 9, looking at how each of those types affect our individual mechanisms.
When we see, like, actual mechanism, I don't know, reaction picture, is that necessarily showing any intermediate steps or not? If there are intermediate steps, does that picture show that? That makes sense.
So, and I think I know where you're going with that. And to your answer, no, sort of. Because you said, in a mechanism, would you see intermediate steps? Absolutely. You would. That's not a mechanism. How do I know that's not a mechanism? curved arrows. A mechanism will show curved arrows. There are no curved arrows in that. So because there's no curved arrows, this is a reaction, okay, which could, if I added curved arrows to it, become a mechanistic step. That's valid. But in this case, we're just saying reactants and products. Until you see curved arrows, this could have intermediates. It could have 20 intermediates. You don't know.
Or not.
You just don't know.
Perfect. That was fine.
From the acid-base perspective, okay, so your question is about atom versus... Damn it, this is all atom effects, so I'll have to add another one here in a second. Here, actually, I'll just add it right now. Okay, so we'll look at ranking those 5 substances. Okay, so when we're thinking about kind of ranking the strength of individual acids or bases, the first thing we need to make sure we do is reference the definition that we're basing it off of. So in this case, we're talking about this as being acidic. Acidic means proton donor. Okay. The problem with evaluating acids based off of their ability to donate protons is that everything we do in organic chemistry is about how electrons move. And if we're going to look at the acid definition as a proton donor, we're not actually referencing anything to do with electrons. So the entire systems that we use to go through and explain how reactions work and how they move from one place to another doesn't work with this definition. And that's why when we talk about trying to rank acid strength, what we tell you to go through and do is look at the stability of the conjugate base. Okay, why? If I draw out a conjugate base, what's the very first thing that I end up addressing? A negative charge, which is electrons. And everything we do in OChem, the entire mechanism world that we have developed to manipulate and understand, is based off of the flow of electrons. Okay, so we typically rank based off of this analysis, our conjugate base. Okay, how does this help us out? If that is more stable, what does that mean? Well, if that is more stable, the reaction is more likely to proceed. That's an arrow. Gemini. Okay? So a more stable conjugate base means our reaction occurs. Well, if the reaction occurs, this species donated more hydrogens, which means it was a stronger acid. Okay? So once we've established that, we could now go through for each of these structures. I think I can pull off color coding on this. We'll call it structure 1, 2, 3, and 4. We could draw out our conjugate bases. So for the very first one, if we donate that hydrogen, we would have a negative oxygen. For the next one, the acidic hydrogen, or the most acidic, is going to be on our nitrogen. For the next one, the most acidic, and I inadvertently dropped myself into a fun little trap on this, Br minus, and then technically our last one, O minus. So if we're being asked to rank these, first and foremost, the process by which you solve is going to become important. What most people do when they go through and see a ranking question is they try and shovel all of these things at once together, which is the complete wrong way to do this. Every ranking question is only asking you to rank 2 things. They're just asking you to do it 5 times. Okay? So let's pick 2 things to rank. I want to rank the difference between structure 1, conjugate base, and structure 2. So what I need to do is evaluate their individual stabilities. Well, the first thing I would go through and evaluate would be the charge. Okay, well, both of them are negatively charged once you've removed that hydrogen. So then I'm going to move to the next thing on the list. You'll notice I say it's an atom effect. Why an atom effect? Well, where's the most reactive thing in both of those cases? It's on a single atom. That's where that charge is located. That negative charge can contribute a little bit to that tailmost carbon, but since there's no resonance, those electrons really aren't being affected by that carbon at all. Similarly, the carbon's not being affected by those electrons. So we're looking solely at where that reactivity is located, and it's going to be on an individual atom. Okay. The next thing I could move, so we could look at size. When we compare oxygen to nitrogen, they're in the same row. So all the way back in Unit 1, we talked about trends on the periodic table and size. And I said, within a row, size doesn't change. Go back to exam 1. Go to the practice or the dry run for the show your work. That's actually the question I put there too. Okay. Size doesn't change across a row. There's not a significant difference, which means when we're looking at an atom effect, if there's no size difference, that's not a difference that contributes to stability. Okay, so we could move to electronegativity. Is there an electronegativity difference between oxygen and nitrogen? Well, yes. Yes, there is a difference between oxygen and nitrogen. Oxygen is more electronegative than nitrogen. What does that mean about its stability? Well, if it is more electronegative, what is it doing with those electrons? It's holding them. If it holds its electrons, how is that affecting the stability? Well, look at the opposite of stability. Less stable would mean it reacts. It would have to share those electrons. So if the oxygen is holding its electrons, that's making it more stable than 2. If it is more stable than 2, what does that mean? That means that 1 was a stronger acid than 2. Okay, that's looking at purely an atom effect. We could throw the sulfur into that argument too. So if we go through and look at sulfur, or our, structure 3, atom effect charge, that molecule is negatively charged. That charge is on that atom, the sulfur. Size. Is size different there? Yeah. Size, sulfur, is larger than, and I'm going to compare it to oxygen because it's the easier one to evaluate. Okay, it's larger than oxygen. What does that do to its stability? Okay, it's more stable because we've now given a larger area for the electrons. So sulfur 3 is more stable than 1. Okay. How do I know sulfur is larger? Well, this again goes to our periodic trends, and back in Unit 1, down a column, size gets larger. Why? We're going to higher energy levels for those outermost electrons. Okay? In each of those 3 evaluations, all we're looking at is an atom effect. Okay? That one atom is holding those electrons, and we found that evaluation. Okay? So we could go through and look at the bromine, but I'm going to erase that because by definition that's an atom effect because there's only the bromide. Okay, so let's go through and take a look at our last one. Okay, and switching all these colors back and forth was bad. I apologize. Let's take a look at that last one. We're looking at a negative charge on that oxygen. Well, if I compare it to the sulfur, okay, what's the difference? Well, in that difference, it's size. Sulfur is larger than the oxygen. So we would predict sulfur to be the more stable because of that oxygen. Okay. What happens when we compare that oxygen in 5 to the oxygen in 1 though? Well, now they're both oxygens. It's still a negative charge. There's no size effect, an atomic size effect, because the charge is on a single atom. Okay. Then we move to an atom effect electronegativity. Well, it's oxygen versus oxygen. There's no difference in electronegativity. Now we can bring in this concept of a molecular effect. Does the rest of the molecule contribute to the stability of those electrons? So what we're asking then is, how does the rest of that molecule affect this? Okay, well, in the case of 5, that molecule affects it because of resonance. What does that resonance do to the stability of that molecule? Well, that makes that molecule more stable. If it becomes more stable, that means it needs to become more acidic, and we'd be putting 5 in here. Okay? You might say, isn't it still negatively charged? Yes, but what we're concerned about is where is that negative charge? Okay, just like when we compared sulfur to oxygen, okay, the sulfur to the oxygen, they're both negatively charged, but because sulfur is larger, those electrons are distributed across a larger area and become more difficult to react. Okay? The same thing is happening when we move to a molecule. Okay? In the molecule, we're now distributing those electrons across a larger area through resonance. So it's the same concept as size, but now we're applying it at a molecule level as opposed to at an atom level. That size is now being distributed through resonance, which is why resonance becomes an important topic. Okay? So the argument that I make in all my videos about these is that we're really just separating out atom versus molecule effects. Okay? Resonance is really just an atom size effect, but now we're looking at how the molecule is allowing those electrons to move or not move. Okay? The other one is the molecular effect induction. Is there an electronegative element somewhere else in the molecule that is now starting to pull on electrons? That pull can be felt further down the food chain. Okay? If that pull is affecting our charge, what we're looking at is an atom electronegativity, an atom contributing to a long distance effect on our negative. That long distance has to move through the molecule, and that's why it's a molecular effect. Does that answer your question, Hassan?
Yeah, that's perfect. I just wanted a little clarification, but that works perfect.
Okay.
That makes a lot more sense.
Okay, good. I will throw in there is that there can be potential exceptions, for instance, between 3 and 5. That is one I don't know off the top of my head. I would have to look at the pKa's for those individual compounds to nuance this. This is a general guideline that works for the majority of cases. We're talking majority, probably 80% of the cases that you'll see. You will encounter that 20% that are exceptions. Those exceptions are things that you should be memorizing, okay, so that you don't have to memorize everything. You're just memorizing that small exception area. Okay? And that's going to come down to the frequency of times you see those. You don't see the sulfur one show up all that often, so it's not that big a deal to memorize. Okay? You will see them pop up every so often. The big one that I would say that needs to get memorized would be the pKa's of your amines and the pKa of that hydrogen. Okay? Why? That hydrogen is more acidic than its partner alkenes or alkanes, but the acidity of that is still relatively low, which means if I want to go through and remove that to make the carbanion, I have to be very careful about the base I choose. Hydroxide as a base won't work. Okay? How do I know it doesn't work? Well, I have context about either the reactions that I've memorized or I've got the pKa's that I've memorized. Okay? Either way works. The pKa for our hydroxide, if we look at that, doesn't align for a favorable reaction, and because I've started down this path, I'm going to have to freaking finalize it. If we go through and look at our hydroxide as the base, negative versus H2O as our conjugate acid, the pKa of H2O comes in about 15. The pKa of the alkyne comes in about 25. Okay? What does that mean for us? Well, our reaction favors the higher pKa because it's less acidic. If I use hydroxide, it doesn't work because the higher pKa is the triple bond protonated. But if I move to NH2 minus, NH2 minus is now a stronger base. Why is it a stronger base than hydroxide? Well, we could go through our list. Charge, same charge, size, same size, electronegativity. Nitrogen is less electronegative than the oxygen, meaning it can't stabilize the electrons as well as the oxygen, which makes it more active as a base. if we go through and look at the pKa for that transition, that pKa comes in about 35. Okay. Now when I look at the reactions and compare the pKa's across the reaction, that's a favorable reaction to occur. Right? So knowing the pKa can really help you predict some of these reactions. Okay, this is why I highly encourage you to do that. Okay, I didn't bother to do it, but I also didn't get an A in organic chemistry. What do you want? Okay, that's your line to go through and decide where that threshold is. Some content you're going to get, some content you won't. Kind of position what works best for you. Okay. Okay. Chapter 6, SmartWork 7. So I've got a request here to go into SmartWork, so I'm going to pause the lecture recording there on that. On this. So what it's asking you to go through and do is these individual steps. Okay, so first and foremost, I do want to say these individual steps are more advanced. So these are not things, how do I phrase this carefully? You are responsible for being able to do these things when you are told to do them. You are not responsible for just being able to think of them out of thin air. Okay, so what you were just attempting to do is do what you're told to do. This is the point of mechanisms. Your mechanisms are supposed to show you go through and do this process. Okay, so we're doing a nucleophilic addition, nucleophile elimination, nucleophilic addition, and a proton transfer. Okay, so if we go in and take a look at our steps. Okay, this is a bit small. Might freak out if I try and zoom in. Or it does nothing. Okay, well that was useful. So, nucleophile addition. So in a nucleophile addition, you need to be losing a pi bond. So if in that first step for our nucleophile addition, because it's an addition, we shouldn't see a pi bond. So if we go through and take a look at your result, no pi bond. So that looks good. Okay. Now we've got to consider all the other pieces behind this. In the process of losing that pi bond, there's the loss of your pi bond with that curved arrow. Fantastic. Okay. How did it lose? You took lone pair electrons and you shared them with the carbon underneath. Fantastic. So that looks good. If we go through and look at the result, of course I'm in annotation mode and I can't go through and actually see what's underneath that for the moment. But from what I can vaguely piece out, that looks okay. Dang it, what were we supposed to do as a second step? I knew I should have written that down. Dang it. Can someone actually tell me what it is? Well, never mind. Change my mind. We then need to do a nucleophile elimination. Okay, so in that next step, we have to do a nucleophile elimination. So the very first thing that I'm going to say is that this box has no arrows. Okay, so if I'm going to move through step 2, what I expect to see in step 2 is the exact same thing as that. Nothing should change because there's no curved arrows. If we look at what you drew in the next box, you changed something. Okay, so you need to make sure that your arrows show that process. Okay, so that's going to be the first thing that you're going to get flagged on for that box being incorrect, is that you have to show the arrows for it. Because it's an elimination, we need to form a pi bond. So when we look at the next box, fantastic, I do see a pi bond. Okay, so now we're going to initiate that process. We want to go through and form that pi bond. So we can have these electrons come down to make the pi bond. Why would I pick those electrons? Well, what's the most reactive thing in that structure? That negatively charged oxygen is the most reactive thing because it's negatively charged. Okay, so it makes sense to have those electrons come down. If we did that, what would happen to that carbon? Well, that carbon should now exceed its octet, which would be bad, and we wouldn't be able to draw a result. So what we want to do is fix that by ejecting a group. Okay, in the nucleophile elimination, you have to eliminate something, form a pi bond. The other part of that is the loss of 2 sigma. Okay? In this case, we're only going to see the loss of one sigma, and that's because the other sigma was already quote-unquote lost. Okay? So there was technically a sigma lost up there to a hydrogen. So that's already been lost. I don't need to worry about that. I need to break a sigma. Okay? If we look at what you drew, you've decided to keep the carbon structure. Okay? So this carbon structure is still there, which means I have to eject something else. Well, ideally what I should be ejecting would be the best leaving group. Okay? That best leaving group is going to be the oxygen because it's the most electronegative. Okay? So that should then leave the structure. Now that I've got arrows in there, I understand what I should be drawing in that third box, okay, as far as structures go. So when we go through to try and match, what I go through and see is I see the same basic patterns. You've got your pi bond. You've got the 2 lone pairs on the oxygen because 1 was used to make the pi bond. So that looks good. I do also see that we have this piece out here. Again, because of the zoom, I can't quite tell. But I do see a negative charge there, and I'm pretty sure SmartWork won't let you put a negative charge there unless you have the proper lone pairs, maybe. Okay, so that oxygen should have 3 lone pairs, which makes sense from where we started on the left. Okay, so cool. What we needed to adjust was in box 2, add those curved arrows. Okay, so now that those curved arrows are in, the products are shown correctly, and now we have to figure out what's going to happen in step 3. Which means, again, we're going to lose all the annotations. And step 3, a nucleophilic addition involving another CH3, CH2, C-. So if we go back to our question, okay, this was another nucleophilic, not elimination, another nucleophilic addition. Because it's an addition, we have to lose that pi bond. Oh, and of course, where everything's drawn, it's going to be difficult to see it. But what we're going to do is lose the pi bond. So cool, I like your arrow. You're breaking the pi bond. What's causing it to break? Another arrow from that carbon. So those arrows look fantastic. That should be good. Okay. The problem that I'm going to see here is that it's very hard for me to evaluate what's happening out here in that box because of where the image decided to place. So I'm going to have to stop and take a look. So there's our new carbon structure in. We broke the pi bond lone pair on the oxygen. All that looks okay. We didn't do anything to the methoxide. Okay, so you left that alone. That could be something that we may have to evaluate here, but mechanistically, that all looks good to me. I see no problems with that. The last step is a proton transfer involving H3O+. So let's go through and take a look at this. Okay, there are a lot of arrows in here. Okay, by showing all of these arrows, you are making the statement that all of this happens at the exact same time. Okay, that should be problematic. One of the kind of tenets of mechanisms is that you want to use the fewest amount of molecules possible to get it to go forward. It is a very rare circumstance that you get 3 molecules interacting at the same time. That's where we get the awkward video comments about threesomes. Okay, so you are showing 3 molecules all interacting at the exact same instant. That is very, very, very unlikely. Okay, so that I'm going to say is going to be the number 1 issue with this. Okay, so if we look to the reaction, it says draw the product formed nucleophilic addition from the nucleophilic addition, which we said was good. Draw H3O+. There's our H3O+. And now add curved arrows for the proton transfer. Okay, so what I see here is admirable. You're saying the electrons, good. You're starting the source there. The electrons would then shuttle the hydrogen, the electrons from the hydrogen to the oxygen. Cool, that makes sense. You're also now saying that this is happening. Okay, so what you are showing is technically 2 separate mechanistic steps. Both of them are acid-base steps, but you've now jammed both of those mechanistic steps into one. That's bad. Okay, you can't do that. So you want to do 2 acid-base steps. That's what you are telling me by showing these arrows. Okay, which would mean if SmartWork wanted you to do that, we would see 2 steps. We only see 1. Okay, which means SmartWork doesn't want you to do that. SmartWork only wants you to do 1. Okay, so now the question is which one? So what we could do, that ethoxide, this methoxide is going to be an issue, I think. We'll have to look at the solution real quickly in a second here. The most important mechanistic step is what you should be addressing. Okay, if we look at your curved arrows, this bottom section, those blue, okay, those, while technically involve an organic molecule because there's 1 carbon here, not very important because this has a whole lot more carbons. Okay, generally speaking, 95% of the time, we want to show the reaction happening with the thing that has more carbons, which means what I had as blue arrows here, you should delete. Those don't belong there. Get rid of them. Is the other acid-base step right? Yeah, you're taking the negative, sharing them with a hydrogen. That hydrogen would exceed its octet, so we break that sigma bond by shuttling those electrons. So what I see is you just need to delete those arrows. Okay? Which would mean when we get to box 4, well, let's actually check this. They aren't adding any more directions into that. Draw the 2 products formed from the proton transfer for step 4. This is where directions come in handy. Okay. Oh, I see what you did here. So number 1, there's our organic structure. We've added the hydrogen to it. Fantastic. Where did that hydrogen come from? Well, it came from H3O+. And because we've deleted the other acid-base step, this hydroxide should actually be H2O. Okay? Well, what is this piece? Well, that piece is coming from, and I don't know if my cursor shows up. This piece is coming from your, what I had called the blue acid-base step, that extra blue step, okay, which we said don't do. Okay? There's actually evidence in how this question, or the directions are phrased to tell us that we should have left it alone. It says draw the 2 products formed from the proton transfer. Well, the proton transfer involved H3O+ and that negative hydroxide, which means that blue structure should be deleted. And I think if you get rid of that, you'll be fine. Okay, so in box 4, you delete that, you make that hydroxide a water, and I think you've got that lined. Let's take a look at the feedback, see where they went through and flagged things. So as I said, that 3rd box looked good. The 2nd box, which was missing our curved arrows, that's why that one's flagged as wrong. The 3rd box, you had that extra blue step, that's why that one was wrong. And then that 4th box, because you drew in the methanol that shouldn't be there. Okay, so if you remember all those things, now we'll go ahead just to verify, just to make sure I don't lead you down the wrong path. There's our 2nd box. We've added the extra curved arrows. Okay. And that 4th box, draw H3O+ and do that reaction. You'll notice they don't have the methoxide that you kicked out. Okay? They don't want you to draw it. I'm going to guess that when you do this one, actually no, because they want you to draw the product. They just want you to draw the product from the nucleophilic addition step. That methoxide that you had drawn in there, which I'll go ahead and real quickly draw in. This piece didn't do anything in the past step. You're just holding it over. Okay, it's carrying over. It is a byproduct of this reaction. It is not a product. So I don't care about it. Okay. This is a bit, one of the kind of unfortunate things with OChem is we don't look at balanced reactions. Typically, we only focus on the chemistry that's important to us. Okay? So that should have covered, I think, everything. Come on. Within that, if we go through and look at the bottom, and yep, there's our water and our protonated structure. So some of it is, most of what I see here is either not adding your curved arrows, or what you're doing is complex mechanisms, but ultimately because you didn't understand that you shouldn't be drawing that extra piece. That extra piece just doesn't get drawn. I wish I had a better explanation than that, but that's all I got. Nope.
Nitrogens?
Yep. Why are the nitrogens the most reactive?
Because they're charged?
Yep. Because they are negatively charged, how might they react?
As a nucleophile?
Mm-hmm. Or
as a base?
Yep. Because they're negatively charged, we get both the aspect of nucleophilicity or basicity. If they go through and act as nucleophiles, they're going to be strong nucleophiles, so they would likely do a substitution at the least sterically hindered place, and we're probably pushing for something like C, okay? Or that direction at least. So if it goes through and acts as a nucleophile, the first thing we might expect to see would then be an NH2 with the lone pair on there, right?
Yeah.
Okay. That was only reacting one NH2. It says to use 3.
Yeah.
So what else could you see?
The other bromine substituted for NH.
Okay, so we could take a second equivalent. And now the third equivalent? Exactly.
Does it... I don't know.
Okay, what if it acted as a base? What would it do then?
It would take a hydrogen or proton.
From where?
Position 1.
Okay, why?
Because it's not hindered.
Okay.
It's steric.
And what would it do? Just you're saying just do an acid-base reaction?
Yeah. Or would it? No. Would it cause another bond or?
Okay. Is a carbon-hydrogen bond particularly acidic? No. Okay. So just running the acid-base reaction is not likely because a carbon-hydrogen bond is not acidic. Okay. What we could go through and do is remove that hydrogen. And as we remove that hydrogen, the electrons shift down to kick out bromine. Okay. And that result, what do we end up with?
A pi bond and then just
Pi bond. Okay. So there we go. We've got a pi bond. We did an elimination reaction while that species was acting as a base. So in one case, we're starting to push elimination. In the other case, we're pushing substitution. And what we're trying to decide is to decipher which of these is going to be best for the overall reaction. Which one is going to account for all of the information supplied. Okay. That was one equivalent of our NH2. What would the second one do?
remove the next bromine.
Careful. Remove the next hydrogen. Okay. So that next hydrogen gets removed. And we now have a triple bond. Yeah?
Yeah. Because the hydrogen pairs up with the bromine?
It's not that the hydrogen pairs up with the bromine, it's that the base pairs up with the hydrogen, which now puts a negative charge on that carbon, which becomes problematic. So those electrons shift over to make the pi bond and force the bromine off.
Okay. So the bromine's just a negatively charged ion?
Yep. So you'd have bromide floating around. Would that be a good thing? Okay, and this is true for both reactions. Both reactions are going to form bromide. Is that a good thing?
What can I use to know if that's good or bad, I guess?
What's the most reactive thing in that solution?
The NH?
With a negative charge. Is bromide floating around better than an NH? Or than a negative nitrogen?
It's competitive, but it's not... I guess it's bad because it's competitive.
Let's see, is Hassan still here? No, I can't call out Hassan with his question. If you remember Hassan's question about ranking stabilities, this is now a ranking stability thing. Which one of those is more stable, bromide or the amide?
The bromide.
The bromide because?
Electronegativity.
Nope.
Is it the size then?
It's the size. Nitrogen's actually more electronegative. That bromide being so much larger is what's stabilizing that negative charge better than the electronegativity of the nitrogen. So is that a good thing? Yeah, that's actually why the reaction will occur. The nitrogen in both of these cases is very reactive. The bromide is more stable, so it's actually reducing the reactivity of our individual intermediates. So, yes, bromide coming off is a good thing. Okay, so back to our... Go ahead.
I was just going to say, is the bromine just a spectator off to the side in the reaction?
Bromide is a spectator off to the side once it has left the structure. It's active in the mechanism when it's connected to the structure, but once it's left, yes, it just becomes a spectator and just chills out on its own. Okay. So both of these, the nucleophile and the base path, have both used 2 equivalents of the NH2. It still says 3. So on the nucleophile side of it, maybe what that third equivalent does is act as a base and remove one of those hydrogens. If it removed one of those hydrogens, we would now have the amide again. And what could the amide do? We have that negative charge on our nitrogen. What would it need?
Positive? Or protons?
A positive found from our CH3I in the very next step.
Oh, okay.
Okay. So that then means that we could do yet another substitution reaction where we put a methyl on there. Well, which hydrogen was acidic? The red hydrogen on our amine or the blue one? In our kind of red structure, our substitution path?
Would be the red one?
Green or blue?
Oh, sorry, green.
Okay, why is that green one more acidic than the blue one? Charge a conjugate base. They'd both be negative. So since they're both nitrogens, the size is the same. Electronegativity, same. No resonance. There's no difference in induction. There's no difference in acidity of those 2 hydrogens.
Okay.
Which then makes this kind of a challenging question. If you don't know which one to deprotonate, which one should you deprotonate? If there's no difference, well, so then that means both of those answers show up and you would be able to select 2 answers? Can you select 2 answers? No.
Maybe.
Damn it. So something weird is going on here. Okay? If we go through and look at the substitution reactions, we're ultimately doing B, C, or D. If we do B, we're using 2 equivalents. Okay? We did 1 equivalent where we put the nitrogen on. We did the second equivalent where we put the methyl on. The question asks for 3. If we do D, we're doing 4 equivalents. We put the nitrogens on, and then we had to deprotonate both. so that they could both act as bases, as nucleophiles. So we would need 4 equivalents of the amide. We're only given 3. In C, we're again 2 equivalents, just like B, except now we've done it on the terminal versus the internal.
Gotcha.
Okay, so none of those really stack out with why it says 3 equivalents of the amide. Okay, and that's why it actually says 3 equivalents of the amide. It's to try and give you hinting towards this direction. So let's drop all the way down to the other option. The base pathway, we used 2 equivalents. Okay, but you'll also notice that we don't have that as an answer choice, right?
Yeah.
What's the third equivalent doing?
Interacting with the next reactant?
Nope.
Taking the hydrogen off of the thing, yeah.
That third equivalent removes the hydrogen. Why does that become important? What do we now have? We have a negative charge which can now find what? The positive charge of our methyl. There's that CH3 from our methyl. There's a triple bond. There's that bend. What structure did we just draw?
A.
There it is. So this is an advanced question for a couple reasons. Number one, we're looking at alkyne production. Alkyne production is really no different than alkene production, so don't let that kind of stress you out. You just have to realize that you have to do it twice. That's why we have 2 bromines, why we have 2 leaving groups. And then it also touches on this kind of aspect of synthesis, and that we're now building a larger structure than what we had to begin with. We're adding carbons to our structure. So this is kind of where second semester goes. Second semester is here's a sequence of reagents, and you have to be able to predict what happens in each of those cases. So this is a advanced question in that respect, and that you have to scaffold these things way, way out there. A lot of this one in particular is going to come with familiarity with the reagents and trying to recognize when these kind of things should happen. If you have 2 halogen leaving groups and you're throwing in a stupidly strong base, you should be doing the elimination pathway. That elimination pathway is going to result in a triple bond. If that triple bond is terminal, that hydrogen is actually fairly acidic and quite acidic when put in the, my recording's going to drop out on me. More acidic when put in the strongly basic environment of the KNH2, that potassium amide. So if you've done practice enough, you should start to recognize when these things pop up. If you haven't done that practice, it does become challenging, and that's where going through and testing your pathways. Let's say it acted as a nucleophile. Where would that go? Well, those answer choices don't really make sense for that. Well, unfortunately, that's a dead end. Go the base route. Okay, and check the other path and see what falls down that path, and maybe the answer choice is there. A lot of OChem is a little bit of trial and error, so you do need to get kind of comfortable playing in that realm. When it comes to an exam, you're right, you don't have a lot of time to play with that. So what should you do? Answer the questions you know how to answer first, and then double back to the ones that are a little bit more challenging to pick up. So I would argue this is one that you either kind of know outright because you've done tons of practice and you're familiar with it, or this is one that you're like, I have no clue what's going on, and you're just going to wait until you have time to answer it. And if you don't get that time to answer it, then you're just guessing and you move on. That's okay. That's one of the challenges in OChem. You will end up guessing.